Friends, very good morning. Today's subject of discussion is synthesis of chloroquine. Before going to that, let us look into the structure of chloroquine. Chloroquine, the basic ring system present in it is a quinoline molecule. It's another way, a quinoline derivative. Chloroquine was discovered in the year 1934 by Hans Andersag. It is an antiparasitic drug which is used in the treatment of malaria. Even today, it is the drug of choice for the treatment of malaria. It also finds its use in the treatment of amoebiasis occurring outside the intestine. Also finds its use in the treatment of rheumatoid arthritis. It is used in treatment of lupus erythematosus. This lupus is a rare disease. It's a metabolic disorder where our own immune system attacks our own organs and damages them. That's why chloroquine is a very useful drug for treatment of different types of diseases. Today's subject of discussion is the synthesis of chloroquine. If I look into the structure, the basic structure is quinoline, and for preparation of quinoline, if I break over here, this part if I take, it will be a benzene ring with nitrogen and chlorine, which are meta to each other. If I take starting material, metachloroaniline, it can serve as a synthon. Now, on this benzene ring system, I have to construct the pyridine ring system. I have to treat with a 3 carbon donor. We proceed like this. I'll take metachloroaniline and treat with formic acid. Nitrogen has lone pair of electrons, as the nitrogen and amino group is in sp3 hybrid form. The carbonyl carbon is the positive center, and as we know, unlike poles attract each other, the lone pair of electrons forms bond with the carbonyl carbon, and to maintain its tetravalency, the carbon kicks off the OH, and I will get corresponding formamide. This formamide which is formed, I will treat with another molecule of metachloroaniline, as this is the electron deficient center. Amino group nitrogen has lone pair of electrons. It attacks on the carbonyl carbon, and pi electrons moves onto the oxygen, and it gets converted into OH, and the H and OH gets removed to form an imine derivative. This imine formed, I'll treat with diethyl malonate. Malonic acid is CH2COOH twice. In this COOH is converted into ester, ethyl ester. It is diethyl malonate. The beauty of this diethyl malonate is that the carbon, central carbon, is flanked between two electrons with the drawing groups. That's why it is acidic enough to lose the proton. Diethyl malonate reacts with the imine derivative which is prepared in the presence of a strong base like sodium hydroxide. OH minus abstract the proton As this is acidic enough to give the proton, and this is basic enough to abstract the proton gets abstracted. As the proton get abstracted, that excess electrons are left onto the carbon, giving rise to a carbene ion. And the carbene ion, which is formed as it is unstable, it attacks on the positive center of the imine ring system. This is electron deficient as there are two electron withdrawing group adjacent to it, and the pi electrons moves onto the nitrogen, and nitrogen gains electron richness. Then again, these electrons moves towards this positive center, and the bond between carbon and nitrogen breaks, and this gets lost. The metachloroaniline which is added has been removed, and in turn I will get corresponding 3 carbon attached to the amino group. If I cyclize this molecule, I can construct a quinoline ring. This is the carbonyl carbon, which is an electron deficient center. In the presence of the electron deficient center, the pi electrons moves towards one carbon because of the electromeric effect created by the carbonyl group. Once these electrons move, this becomes a carbene ion, an electron rich carbon, and this is an electron deficient carbon, and both are adjacent to each other. It attacks on the carbonyl carbon, and ethoxy, being the easy leaving group, gets kicked off, and it loses as ethanol, and the cyclization occurs. As these electrons are moved over here, the carbon has gained positivity, and to satisfy this electron deficiency, the carbon hydrogen bond breaks, and these electrons are utilized for satisfying this positive center, and H plus goes away. Then aromatization occurs. The nitrogen hydrogen bond breaks, and these electrons are utilized to form the bond to the adjacent carbon. And as it is already tetravalent, it has to maintain its tetravalency, this carbon, and hence it kicks off the pi electrons into the adjacent carbon. And this carbon has to maintain its tetravalency. That's why pi electrons moves on to oxygen. O minus combines with this H plus, and it gives a quinoline ring system with COOET group and OH group attached to 3 and 4 position. Now, if I remove this COOET, I'll get 4-hydroxy 7-chloroquinoline. I hydrolyze this molecule by treating with a strong base, and it loses ethanol, and it gives rise to carboxylic acid. If we strongly heat it, it loses carbon dioxide and get 4-hydroxy 7-chloroquinoline. We can treat with POCl3, a chlorinating agent. The OH gets replaced by chloride ion. I have got corresponding 4,7 dichloroquinoline. Here we have constructed the basic nucleus of the chloroquine. Then we have to prepare the side chain. Let us look into the preparation of side chain. I have diethylamine, and I will treat this with ethylene oxide. This is the positive center as the adjacent oxygen is electron deficient. Nitrogen has lone pair of electrons. It attacks on the positive center, and it has to maintain its tetravalency. The bond breaks and it opens up the ring system. I got diethyl amino ethanol. This OH, I'll get it converted into chloro group to make it easy living. That's why to do that I treat with thionyl chloride, a mild chlorinating agent, and OH gets replaced by chlorine. The diethyl amino ethyl chloride which is formed is treated with ethyl acetoacetate. Ethyl acetoacetate in the presence of sodium ethoxide. The ethoxide ion abstract the proton and the excess electrons are left onto carbon, giving rise to a carbene ion. The carbene ion attacks on the electron deficient carbon to which the halogen is attached. The chlorine being the easy living group loses as chloride, and that chloride ion combines with sodium to lose as sodium chloride, and I will get corresponding bond formed between the ethyl acetoacetate carbon and the diethyl amino ethyl carbon. I hydrolyze this using the sodium hydroxide. I will get corresponding carboxylic acid with the loss of ethanol. Heat it strongly, it loses carbon dioxide and it gives corresponding diethylamino firing pentane 2-one. When it is treated with amino group, it attacks on the carbonyl carbon and pi electrons shift onto the oxygen. The corresponding carbon nitrogen bond is formed and the carbonyl group has converted into alcoholic group. This has been reduced by treating with hydrogen and nickel. The alcoholic group gets reduced to alkyl. We have generated the side chain diethyl amino 2-amino pentane. And the side chain which is formed is again treated with the nucleus formed. If we condense both the nucleus and the side chain, we can generate chloroquine. We take the formed nucleus, that is 4,7 dichloroquinoline, and treat with 2-amino pentyl diethylamine. This amino group being in sp3 hybrid form, the nitrogen is in sp3 hybrid form. It has lone pair of electrons. That's why it attacks on the carbon to which the chlorine is attached owing to its electron deficiency. And the chlorine gets kicked off. H plus from NH2 and Cl minus from here combine together to lose as HCl, and the carbon nitrogen bond has occurred and a chloroquine has been prepared. This is the method of synthesis utilized for the synthesis of chloroquine. Next class, we can deal with other molecules. Till then, have a nice day. Thank you.